Heat and calculations. In this lesson, we're going to look at not just how to do calculations with heat, but also kind of the history of heat. As with a lot of the history parts in this course, it's one of those things that's not essential, but I think is helpful to understand where things came from and how we think the way we think. And it also just gives you a good background on what heat is. So the earliest views of heat were what we call the caloric theory. So this is mid-1800s. And so the caloric theory stated that heat was a fluid called caloric that would flow from hot to cold. I mean, this makes intuitive sense if you think about it. Like, look at a fire. You see kind of wavy looking stuff above the fire. Think of like the mirage effect on a hot parking lot in the summer. Think about when you touch something cold, it really does feel like the heat's flowing out of you. And so that's why they thought of it as a fluid. This theory, though, had two major issues. The first one being friction. If I rub my two hands together, they get hot. It's not like one of them's hot and one of them's cold and I'm transferring heat between the two. They're both the same temperature. But as I rub my hands, I'm creating heat. Where is that heat coming from? If it's a fluid, we don't know. Okay? So also, if it's a fluid, then it had to be finite. So Count Rumford showed that when they were using cannon bores, basically he blunted it so that it wouldn't cut in, but it would keep making friction. And he showed that it would go for over 2 hours and never without giving off heat. Sorry. It would go for 2 hours and never stop giving off heat. And so they knew something else was going on here. So that's where James Joule comes in. And he designed several experiments that show that heat was related to mechanical and kinetic energy. This is his famous one. So the people who had the best thermometers at that time period were brewers, people who made beer. And so what he did is he took a brewing tank, put big paddles in it, and a thermometer. And he showed that as this weight fell and spun the paddles, that it actually caused the temperature inside the container to go up. And he's like, well, that temperature has to come from somewhere. It must come from kinetic energy. And so he was able to kind of prove that heat was a form of energy. They did not yet know that it comes from the kinetic energy of the molecules in the water, but he did realize that it's more related to kinetic and mechanical energy than it is a fluid. And so this is essential. We now know that heat is a form of energy. And so this is 1800s that they're figuring this out. All right. I've already mentioned briefly the kinetic theory of matter. Basically saying molecules and atoms, for that matter, that make up all things have kinetic energy. Constant random motion. We talked about diffusion in the last lesson. And the motion is random in both its direction and its magnitude. So this guy may be moving fast while this one's moving slow. And so that's also somewhat randomized. That when we talk about temperature, we say it's the average kinetic energy of a sample. Meaning, think bell curve. That most of the molecules in a glass of water at 25 degrees Celsius are going to be moving around kind of a central kinetic energy, whatever that temperature translates to kinetic energy. But there are going to be some molecules that are moving faster, and there are going to be some molecules that are moving slower. So kind of think bell curve there. All right, so these discoveries led to the following. Temperature is defined as the measure of the average kinetic energy of an object. We've already talked about that. And that heat transfer that kinetic energy. We also talked about that in the last unit. There are three types of heat transfer. First, we have conduction. That's direct contact. You put a pot on the stove, and assuming you don't have an induction cooktop, it is actually conduction. It is directly contacting the surface, and that creates heat. Either it's getting the fires directly touching it on a gas stove, or you're directly on an electric burner. Second one, convection. It's the idea of heat transfer by flowing fluid, like we blow over a hot spoon. We're blowing over, that's a flowing fluid, and it carries some of the heat away. Okay, think about a breeze on a hot day. It cools you off because it's carrying some of the heat away. That is convection. Okay, and then we have radiation. This is some type of transfer by electromagnetic waves. I believe induction cooktops work by some form of radiation causing molecules to vibrate, but that's a different topic. All right, units of heat. Two primary units of heat, calorie. So calorie, once again, we said that heat's a form of energy. So we measure the energy in food by calories, which is a little different than which we'll get to in a second. So a calorie is defined as the amount of heat required to heat 1 gram of water 1 degree Celsius. So not a whole lot of heat. All right. A dietary calorie is equal to 1,000 of these, and it's capital CAL. It's a dietary calorie. The SI unit, though, is the joule, and 1 calorie is 4.18 joules. A calorie is pretty small, and a joule is even smaller, because it takes 4 of them to equal a calorie. We just simply can convert them back and forth, just like we do any other unit. So if I have a Hershey's Kiss, that's 22 dietary calories. I can do my conversion from dietary calories to calories, and then calories to joules, and then I get 92,000 joules or 92 kilojoules of energy contained in that one little Hershey's Kiss. So different materials deal with heat differently. And the measure of how they do this is called specific heat. So think about it. You know, if I've got hot water in an insulated mug, I probably don't feel it. But if I have hot water in a thin metal cup like this, I'm going to feel that heat go through that cup to my finger very quickly. That the metal is going to transfer and warm up faster and transfer that heat faster than an insulated cup would. Like a styrofoam cup or the ceramic mug even, or the wooden spoon. How fast a wooden spoon is not going to get hot. You can hold that wooden spoon in hot water all day, and the end of the spoon that you're holding is probably never going to get hot. So it's just something we need to be aware of. How this is talked about is called specific heat. And so specific heat is given the symbol C, and it has this really crazy unit of mass over heat over mass and temperature. So joules per gram degree C, or joules per gram Kelvin if we're using the SI unit of temperature. Like I said, sometimes you'll see Kelvin there instead of Celsius. And so when we're talking about specific heat, we would say that something that has a higher specific heat value is slower to absorb and release heat. So for example, water has a relatively high specific heat value, 4.18, as opposed to air. That's why, like in the fall, or even depending on where you live in the summer, you know, at night the air can get cool, but if you jump in the pool's still warm. And so you get that experience of the heat difference there. And so the water, you know, same thing in the morning. Like if you jump in a pool first thing in the morning, the air may be warm, that pool is going to be cold because it's going to take longer for the water to warm up here than it is for the air to warm up. And then it's same thing's opposite the other way. Air cools off faster than the water does. You know, think about, you know, air temperature versus like the outside of your car. Just the sun hitting that car is going to cause that car to heat up a lot faster than the air would. Same thing with cold. It's going to cool off faster than the air would. The amount of heat absorbed or released by an object can be determined by the following equation. The equation is Q equals mc delta T. All right, so let's run through what all these letters mean in this equation. So Q is the heat. Once again, we call heat enthalpy, and it's given the letter H, but yet some reason when we do this equation it's Q. I don't know why. I just know that it's the same thing as H, it's the same thing as delta H. It's just what it is. So it's Q in this equation. Positive means absorb, negative means release, just like with delta H. M is the mass of the sample, and it has to match the units that you have in C, the specific heat. And so all of these need to match the same unit. So like if the unit on C is calories, then heat needs to be in calories. If it's joules, this needs to be joules. If it's grams, mass needs to be grams. If it's kilograms, the mass needs to be kilograms. If it's moles, then we got to still do the same thing. All right, C is specific heat, and unfortunately, specific heats can have various units. Delta T is just like we saw with delta H. It's always final minus initial. It's always T2 minus T1. A positive change meaning the temperature went up, a negative change meaning the temperature went down. So let's look at exactly how I would do one of these questions. So how much heat will be needed to heat 355 grams of water from room temperature to 100 degrees Celsius? And then you're given the specific heat value. You'll always be given specific heat values. All right, here's kind of my problem solving method that I use when I get to any of these types of questions. And we'll see this in the next couple of units as well. So first thing I want to do is I want to identify the variables that I have. I'm given a mass, 355 grams. I'm given an initial temperature of 25 degrees. I'm given a final temperature of 100 degrees. And I'm given the specific heat of water. So I've identified what I've got. So for me, if I was doing this on paper, I would write M here, I would write T1 above here, and I would write T2 above here. I would just simply identify what variables have I been given. I write down my equation. I always write down the equation without any numbers in it first. It clarifies things, it slows me down, and it helps me to put things in the right spot. So Q is what I'm looking for. I'm looking for heat. So then I just plug in everything else. Q is what I'm looking for. M is 355. C is 4.18. And the temperature is T2 minus T1, or 100 minus 25. Put all that in the calculator. You get 111 kilojoules of heat is what you need. So that's simply what I call essentially plug and chug. Find your equation, plug in the variables that you found, and then chug out an answer. All right, moving on to example 2. What is the final temperature after 50,500 joules are removed from 350 grams of aluminum? That starts off at 25 degrees Celsius. So with the equation Q equals mc delta T, you can be asked to solve for any variable in the equation. You can be asked to solve for Q, for M, for C, for any of the temperatures. And we're solving for one of the temperatures here. So once again, same set of steps. Identify your variables. Q is negative because it's removed. M is 350 grams, T1 is 25 degrees Celsius, and then you can find the value on the chart earlier for the C value for aluminum. We got Q equals mc delta T. Don't know why it's showing up as a D there, but anywho. All right, so you plug in everything and you work your algebra. This one's a little bit trickier algebra-wise because you got that T2 there. So you can move both of these over here and you get negative 161 equals this, and you get negative 136 degrees Celsius, aka cold. All right, so that is the basics of using Q equals mc delta T and the basics of heat. In the next lesson, we'll look into what is called calorimetry, where we're going to take this basic idea of calculating heat and take it up to the next level.